One of the toughest diagnostic challenges you face today is isolating those intermittent electrical system problems, or trying to find a performance problem that only shows up on the road after driving for half an hour. What about drivability problems caused by conditions that don't set a trouble code, such as momentary glitches or sensors out of calibration, leaving you to monitor individual sensor circuits? More and more, conventional test equipment and scan tools alone are not capable of providing you with the information necessary to diagnose today's cars accurately the first time. John Fluke Manufacturing Company, a recognized leader in compact professional electronic test tools, has combined the diagnostic power of a lab scope with the versatility of a handheld digital multimeter to bring you the Fluke 97 Auto Scopemeter, the professional's choice for precision diagnostics. Its 50 megahertz bandwidth, 25 million samples per second, and 40 nanosecond glitch capture display momentary voltage fluctuations less powerful scopes often miss. Its dual trace capability lets you read two signals simultaneously, one on channel A, the second on channel B, providing a clearer comparison of cause and effect relationships. AutoSet provides you with an easy way to display a waveform on screen fast. Digital storage capability combined with a unique hold feature lets you watch and review voltage changes throughout entire sensor sweep tests, and the zoom feature lets you move in for a closer look at questionable waveform discrepancies. And Scopemeter's easy hookup and menu-driven interface make it your first choice for electronic diagnosis. Hello, I'm Dave Hyatt. In this program, we'll examine how the Fluke Scopemeter can make your job easier and more profitable. You'll become proficient in using Scopemeter for diagnosing common and some not-so-common automotive diagnostic problems. You'll learn how to use Scopemeter to view and diagnose AC generating components such as ignition pickups and ABS wheel sensors. How to view and diagnose digital signals that vary in frequency, pulse width, amplitude, or a combination of the three. You'll learn how to use Scopemeter to read and diagnose non-repetitive signals generated by sensor sweep tests. You'll learn how Scopemeter's dual trace function allows you to watch and compare dependent electrical signals, such as an ignition reference signal and an injector signal. And you'll learn to use Scopemeter to examine electrical interference and signal noise in electrical signals. Your home study program includes this videotape, a student workbook, an automotive waveform directory, and a waveform simulator. The videotape is time-coded, and each lesson in the workbook is referenced to the time coding, so you'll always know just which video exercise corresponds to the workbook. The simulator generates various electrical signals for you to use in the simulator exercises. The lessons in this program are broken into simulator and on-car exercises for using your Scopemeter. Each lesson covers a specific waveform category common to automotive electrical systems. Follow these lessons in order. Each lesson builds on the information and procedures you learned in the previous lessons. Each simulator exercise in the video program has a simulator lab sheet in your student workbook. Each on-car exercise has a diagnostic worksheet. Watch each lesson in the videotape, then go back and perform each exercise using your workbook and Scopemeter. At the end of each simulator exercise or on-car exercise in the videotape, you'll see a title screen that tells you to stop the tape and go to the lessons in your workbook. Your workbook has information sheets with additional diagnostic procedures and background information, expanding on the diagnostic procedures covered in the video. You'll also find reference material for diagnosing specific waveforms and components using Scopemeter. Your workbook contains a glossary of terms common to electrical diagnosis and oscilloscope procedures. Use it to find any terms you don't understand. The first page of each simulator exercise in your workbook shows you how to configure your simulator for that exercise. Your program comes with a pretest, a final evaluation, and mini-tests for each lesson in the program. The pretest is to help you pinpoint weak areas in your knowledge of using oscilloscopes for automotive electrical diagnosis. Each lesson has its own mini-test to help you evaluate your progress from lesson to lesson. Once you're sure you understand the procedures and principles for a lesson, go to the next lesson in the videotape. When you finish the entire program, complete the final evaluation in the back of your student workbook and send your answers into Fluke's home office for grading. The address is listed in your workbook. Once your test has been satisfactorily completed and received by Fluke's testing facility, you'll receive a certificate of completion. Now stop the tape and take the pretest in your student workbook. Then use the answer key in the workbook to see how well you scored. Let's begin by looking at what came with your Scopemeter, getting an overview of its physical appearance and the terms used to describe them. Scopemeter comes with 3 test probes, 2 BNC to banana jack adapters, 3 alligator clips, 3 test point connectors, 3 4mm banana plug adapters, an RPM 80 inductive pickup, an AC charging adapter, a cigarette lighter power adapter, and a set of back probing pins for making electrical connections. Now, your kit may look slightly different due to enhancements. If any of these items are missing, contact your Fluke distributor. Your Scopemeter comes with a NiCad battery pack and a 12-volt adapter to provide you with full portability and flexibility. To charge the batteries or to operate your Scopemeter from standard AC current, make sure you set the charger to 115 volts. Plug the power adapter battery charger into the external power jack and a regular wall socket, and charge your Scopemeter for at least 16 hours when you first open the box to bring the batteries to a full charge. The red BNC jack is for channel A's probe. The gray BNC jack is for channel B's probe. The black banana jack accepts a common ground lead. The red banana jack accepts a lead for testing diodes, measuring resistance in millivolts, and is the output for Scopemeter's built-in signal generator. If you've ever used a lab scope, you know they use a series of dials, switches, and buttons to move from setting to setting. Each setting has its own dial, switch, and button setting, which makes most lab scopes rather large and bulky. Scopemeter's compact size is a direct result of its menu-driven interface. Each keystroke activates a menu command that walks you from one feature to the next. Each menu selection allows you to fine-tune Scopemeter's settings until you have the precise setting necessary for the test you want to run. Using a menu-driven interface reduces the number of keys necessary for operation. There are 2 types of keys on the keypad: hard keys and soft keys. The hard keys are labeled. Their functions remain the same no matter what mode Scopemeter's in. For example, the on-off key always turns Scopemeter on or off. The scope key always sets it to the oscilloscope mode. The soft keys, on the other hand, change function based on the mode you're in. The bottom display identifies the soft key functions. The second soft key from the left turns the probe calibration pop-up menu on. The up-down arrows change the selection in the pop-up menu, and pressing the Enter soft key activates the selection. The large bold dot shows which mode is active. Message bars display information about a warning or a condition taking place, such as an impossible request. When you switch to the scope mode, the functions of the soft keys change to reflect the new mode. Now, the second soft key from the left turns free run on and off. A little later, we'll see how that change affects the waveform you're working with. The top display lists the settings in effect. The top row shows the voltage scale, type of voltage coupling, and probe settings. Information for channel A is on the left, channel B on the right. The bottom row provides time-based settings for both channels and trigger information. The right menu displays information about the mode in effect and provides you with a means to make selections. Now that we're familiar with some of the terms we'll be using and the features of Scopemeter, let's start learning how to use it. We'll start by performing a master reset. Make sure Scopemeter is off and remove any test leads. Press and hold LCD. Press and release on-off. Then release the LCD button. You should hear a double beep. That tells you the master reset was successful. If you don't hear a double beep, repeat the procedure. Your Scopemeter should power up in meter mode after a master reset. If your room lighting makes the LCD readout difficult to see, turn the backlight on. Press the backlight soft key to toggle the backlight on and off, and the up-down arrow keys to adjust the contrast. A master reset also adjusts Scopemeter to use a 10-to-1 probe. Since you'll be working with a 1-to-1 probe, you'll need to readjust the probe settings. Turn Scopemeter off again and hold the far left soft key down while you press and release on-off. Scopemeter should beep once and come on in the 1-to-1 mode. For ease of viewing, switch from a quadrant grid to a border grid. Here's how. Press Scope, then press LCD. Now press the Grid soft key to bring up the pop-up menu for the display. Use the up-down keys to choose Border Grid, and press the Enter soft key to activate. Now that you've become familiar with Scopemeter and its accessories, you're ready to perform the master reset and probe setup yourself. Make sure you're thoroughly familiar with both procedures before going on to look at your first waveform, an AC sine wave. Now stop the tape and go to the master reset and probe setup section in your workbook. In this lesson, you're going to use Scopemeter to view your first waveform, an AC sine wave, using the built-in signal generator to generate the signal. You'll learn how to read a basic oscilloscope waveform and become familiar with some of the terms involved, such as voltage scale and time base. You'll also use the simulator included with Scopemeter to produce another type of AC waveform, a sawtooth waveform. And you'll learn how trigger level and slope affect how you view a waveform. Finally, you'll learn how to read and diagnose the waveform typically produced by automotive components that generate AC signals. Make sure you watch this section all the way through before trying it on your own. You'll be told when to turn the tape off and go to the signal generator exercise in your workbook. For this exercise, you're going to use Scopemeter's built-in signal generator to display an AC sine wave. You'll need to use the red probe for channel A and its adapter. Align the notches in the BNC probe adapter with the tabs in the channel A BNC jack. Push the adapter onto the jack and turn the collar clockwise to attach the adapter to the jack. Plug one end of the lead into the adapter, the other end into the red signal generator jack. Now you're ready to generate the signal. Turn your Scopemeter on. Press Scope to select the scope mode. Press Chan AB and press the Channel B soft key twice to turn Channel B off. Press Special Function. Then press the Generate soft key. A pop-up menu should appear listing several signals available through Scopemeter's internal signal generator. Choose Sine Wave using the up-down arrows, then press Enter. Press Scope again to change the soft key's functions. Then press Auto Set to bring the voltage scale and time base into adjustment. Auto Set tells Scopemeter to select the voltage range in meter mode and select the voltage range and time base in scope mode automatically. What you should be looking at is an AC sine wave. Well, great, but what does that mean? In order to understand what a waveform's showing you, there's a couple of principles you should understand about oscilloscopes. All oscilloscopes display voltage over time. That is, voltage changes over a pre-selected period of time. By changing the voltage scale and time base, Scopemeter can capture and display voltages and time slices that range from almost nothing to huge quantities. Voltage levels range from as little as 1 millivolt per division up to 100 volts per division. and time-base values from 10 nanoseconds, or billionths of a second per division, to 60 seconds per division. If you take a look at the top display, you'll see a voltage and time value for each division of the display. This scope meter picked levels of 200 millivolts and 500 microseconds for each division on the scope display, though your readings may vary. One point to remember is that this signal has a much higher frequency than most typical automotive signals. Let's start by looking at the voltage scale. By counting the division marks, you see that the voltage rises 2.5 divisions and falls 2.5 divisions from the center division. So the voltage you're looking at varies regularly from 500 millivolts positive to 500 millivolts negative. That's a peak-to-peak voltage variation of 1 full volt. To display the entire waveform, the screen must display slightly more than 1 volt. By counting the divisions, you see that the display is 8 divisions from top to bottom, 1,600 millivolts, or 1.6 volts. Let's see how changing the voltage scale changes the appearance of the waveform. Press the V, or volts end, of the voltage scale hard key to increase the voltage scale for channel A. Now, what changed? The waveform is shorter, but did the voltage actually change? Check the top display. Now the vertical divisions are equal to 500 millivolts, so the voltage is still the same as before. The only difference is the scale you're reading it on. Now let's look at the horizontal divisions, time. The display is 10 divisions wide, and each division is 500 microseconds, or 500 millionths of a second wide. So what you're watching is how the voltage changes over the course of 5,000 microseconds, or 5,000ths of a second. Let's see what happens when you adjust the time base. Press the S, or second side, of the time base selection hard key to increase the amount of time between divisions. Since you're increasing the amount of time you're viewing on the display, the number of oscillations you see increases also. The waveform you were looking at was 5 milliseconds wide, 500 microseconds per division. Increasing the time base to display 10 milliseconds increases the amount of signal you're looking at. Since the time base increased, naturally you'd see more oscillations. But the display doesn't change size when you increase the time base. Instead, Scopemeter compresses the waveform. So rather than 5 milliseconds, you now see 10 milliseconds on the display. That's why increasing the time base lets Scopemeter display more oscillations, twice as many as before. Each time you press the second side of the time base selection hard key, you increase the time base, thus increasing the number of oscillations. But that reduces the amount of detail or resolution you're displaying. In addition, each time you increase the time base, you're reducing the number of samples a digital scope takes per second. Now, this is an important point to consider, and here's why. Each time a digital scope takes a voltage sample, it draws a dot on the display. By combining and connecting the dots, it displays a waveform. But suppose it only took a few samples. What would happen to the waveform? The waveform could change drastically if the number of samples was too low. More importantly, anything that occurred between the samples recorded would be lost. That's why it's important to keep the sampling rate as high as possible. Scopemeter's high-speed glitch capture prevents you from losing events that occur between the dots. So, what's the best setting for time base? One that displays 1 to 2 complete cycles of the signal you're checking. There's one last topic we should look at for understanding oscilloscopes: trigger. And trigger breaks down into 3 categories: trigger level, slope, and source, all of which sounds a lot more complicated than it is. Trigger level is a voltage that tells Scopemeter when to begin tracing a waveform. Let's say you set trigger level at 2 volts. Scopemeter won't start drawing a waveform until the voltage level crosses 2 volts. If the voltage never gets past 1.5 volts, Scopemeter never displays a waveform. If the voltage never drops below 3 volts, same thing, no waveform. But as soon as the voltage crosses the 2-volt threshold, Scopemeter begins drawing a waveform. capturing a window of time. The waveform pattern continues all the way to the end of the display, where it stops, until the voltage crosses the trigger level again. Then Scopemeter begins tracing the voltage again. But suppose the voltage you're reading fluctuates between 1 volt and 3 volts. At this point, Scopemeter could begin its trace when the voltage was increasing or when voltage was decreasing. And that's where slope comes in. By specifying a trigger slope, you're telling Scopemeter to begin its trace only when the voltage crosses the trigger level in a specific direction. For example, if you select a positive slope, Scopemeter begins tracing the voltage when it crosses the 2-volt level on its way from 1 volt to 3 volts. Crossing the 2-volt level going from 3 volts to 1 volt won't trigger the trace. On the other hand, if you set a negative slope, Scopemeter ignores the voltage as it increases from 1 volt to 3 volts. It won't begin to trace until the voltage crosses the 2-volt level going the other way. The final category, source, determines which electrical signal you use to trigger the waveforms. You can trigger from either channel A, channel B, the signal generator, or an external source. Your shop's ignition oscilloscope is a good example of triggering a signal from an external source. The signal being displayed comes from the secondary ignition pickup. All secondary voltages are displayed through this channel. The number 1 plug wire pickup is the signal source that triggers and maintains the order for the cylinders displayed. Triggering the signal from the number 1 cylinder keeps cylinder number 1 first on the display. Most oscilloscopes won't begin to display a trace until the number 1 plug fires, triggering the signal. Switching to the primary ignition display changes the channel you're viewing, but the primary pulse still triggers from the number 1 pickup. And this is an example of external trigger. But most of the examples you'll be looking at trigger internally. That is, from the signal or one of the signals you're viewing. Now that you've looked at voltage, time base, and trigger, perform the signal generator exercise for Lesson 1 in your workbook. Make sure you're thoroughly familiar with this procedure before going on in the video. Now, stop the tape and go to the signal generator exercise for Lesson number 1 in your workbook. In this exercise, you'll use what you've learned so far to view and examine an AC waveform. Now watch this section all the way through before trying it on your own. You'll be told when to turn the tape off and go to the simulator exercise in your workbook. Connect Scopemeter to the simulator and set the simulator the way it shows in Lesson 1 in your workbook. Turn Scopemeter on and use what you've learned about voltage scale and time base to adjust the waveform on the display. For the most accurate readings, set the time base to display 1 or 2 cycles. If you make a mistake during a procedure, don't worry. Pressing undo lets you back up through the procedure. You can undo up to the last 10 keystrokes you performed. To display this waveform, the Scopemeter shown is set to 500 millivolts and time base is 10 milliseconds per division. Now your settings may vary slightly. This is an AC voltage signal too, but it looks a bit different from the signal you looked at earlier. That was an AC sine wave, but most AC waveforms you'll run into in an automobile won't look that smooth. Most of them, such as a distributor pickup or a permanent magnet vehicle speed sensor, will produce a more pointed waveform. These are still AC signals, but because they come to a point, their peaks are better suited for generating precise timing signals. You'll use this sawtooth waveform to see how adjusting the trigger level and slope changes the way you view these waveforms. Use Move to move the waveform 1 division to the right. That will make this exercise easier to see. Press Trigger and use the up-down arrows to set the trigger level to 0. Notice that the waveform begins its trace in the middle of its upward sweep. That's because the trigger level is at 0 volts with a positive slope. The trigger icon confirms a positive slope. Watch the waveform and press the slope soft key. See the waveform change? It's still starting its trace at 0 volts, but now it's on the downward sweep because the slope is negative. Check the trigger icon. It's reversed, signifying a negative slope. Switch back to positive slope and try to increase the trigger level. The signal isn't really moving. Scopemeter's just starting to trace the waveform at a higher voltage. If you keep increasing the trigger level, you'll soon exceed the voltage signal being generated. What happened? Earlier we said the Scopemeter wouldn't display a waveform if the signal didn't cross the trigger. How come you still have a waveform? Well, that's another feature of Scopemeter. Free run. Press Scope, and you'll see free run is on. If you turn free run off, the display freezes. It continues to display the last trace. Scopemeter is waiting for another trigger to begin tracing another waveform. With free run on, Scopemeter displays a waveform even without a trigger level. But without a trigger level, Scopemeter doesn't know when to begin to trace the waveform. The starting point varies, making the waveform appear to wander. Trigger allows you to decide where the waveform begins, so you can view a waveform in the form that makes it easiest to read and diagnose. Adjust the trigger on your Scopemeter to 0 with a positive slope and move the waveform back to the edge of the display. Then you're ready to save your setup. To display any waveform, you must make a set of adjustments, including voltage scale, time base, trigger level, and so on. Each specific configuration is called a setup. One of Scopemeter's features is its ability to save and recall up to 10 setups. The setup for this waveform is similar to the setup for all AC generating sensors operating at slow speeds, including distributor pickups, crank sensors, and anti-lock brake system wheel sensors. Save this setup in memory number 1. Here's how. Press Setup, then press the Save soft key. A pop-up menu appears giving you a list of 10 setup memories. Use the up-down arrow keys to highlight Setup 1, then press Enter. Your current setup is stored in memory to recall whenever you need it. A word of warning. A master reset does more than just bring Scopemeter back to factory default settings. It wipes out anything you've stored in memory. Never use the master reset unless you're prepared to lose everything stored in memory. Well, now that you've learned about trigger and how to save a setup, you're ready to perform the simulator exercise for Lesson 1 in your workbook. Make sure you're thoroughly familiar with these procedures before going on in the video. Now, stop the tape and go to the simulator exercise for Lesson 1 in your workbook. In this exercise, you're going to examine an actual AC signal generated by an electronic ignition distributor pickup. This is a common test procedure for a vehicle that won't start to verify distributor pickup output. Watch this section all the way through before trying it on your own. You'll be told when to turn the tape off and to go to the on-car exercise in your workbook. To read this signal, you'll need to remove the distributor cap and rotor and disconnect the pickup from the electronic ignition module. Connect Scopemeter's Channel A probe and ground lead to the wires from the distributor pickup. It doesn't matter which lead you connect to which wire. Turn Scopemeter on and recall the setup you stored in setup memory number 1. Press Setup, then choose Recall. Use the up-down arrows to choose Setup 1. Then press the Enter soft key. That restores Scopemeter to the settings you used to read the AC sawtooth waveform. Check the right menu. Look for a flashing cursor. It should say No Trig, telling you Scopemeter's ready and waiting for a signal. If it says Hold, press Hold Run. The highlight should change to No Trig. Crank the engine. You may have to change the voltage scale at time base, since cranking speed and the number of cylinders affects the voltage level and the time between cycles. Once you have between 1 and 4 cycles displayed, press Hold Run. That freezes the display for detailed examination. Let's see how to use the waveform you've just captured to diagnose an ignition problem. One of the first things you're looking for is a signal. No signal indicates a broken wire or shorted pickup coil. As long as you have a signal, check the signal amplitude or voltage level. Look for even peaks. One pulse much lower than others indicates a chipped or broken reluctor tooth. If the amplitude fluctuates, the distributor shaft could be bent. The amplitude should reach at least 300 millivolts, sometimes called the threshold level. Any lower could indicate a wide air gap, a weak magnet, or a slow cranking speed. Once you have the voltage scale and time base set to view this waveform on car, use these settings to replace the setup in memory number 1. So far you've been running this test with the engine cranking. One thing to remember is that there'll be a huge increase in frequency and amplitude with the engine running. In this lesson, you've looked at AC electrical signals. Now you're ready to perform the on-car exercises for Lesson 1 in your workbook. Once you finish the exercises, answer the review questions at the end of Lesson 1. If you aren't comfortable with the information covered in this lesson, go back and review those sections giving you trouble. Make sure you're thoroughly familiar with the procedures covered in Lesson 1 before going on in the program. In the next few lessons, you're going to look at more typical automotive signals, DC pulse trains. Now, stop the tape and go to the on-car exercises for Lesson 1 in your workbook. Next, you'll see how Scopemeter can help you examine and diagnose pulse train waveforms. When examining pulse trains, there are 3 possible areas for variation. Frequency, which is the number of cycles that take place over a specific time, pulse width, which is the time a signal is on, and amplitude, which is the voltage level. In this lesson, you'll examine circuits which provide a variable frequency signal. The pulse width and amplitude remain constant. These circuits include Ford map sensors, AC Delco and Hitachi mass airflow sensors, Hall effect sensors, and optical distributors. Scopemeter's meter function allows you to read voltage, frequency, and duty cycle measurements and see how those measurements relate to one another. And you'll learn to use Scopemeter's record and min-max features to capture momentary glitches in a sensor signal. Watch this section all the way through before trying it on your own. You'll be told when to turn the tape off and go to the simulator exercise in your workbook. Set the simulator up as shown in the simulator exercise for Lesson 2 in your workbook. Attach Scopemeter's Channel A probe and ground lead and turn Scopemeter on. You're going to use Scopemeter's Auto Set feature to adjust the levels on this signal, but first you have to adjust the settings for Auto Set. Press Setup, then press the far right soft key. That brings up the Auto Set pop-up menu. Turn off Coupling AC. That keeps Scopemeter from always selecting AC coupling when you press Auto Set. Choose Cursor and Signal Generator from the Turns Off submenu. That turns the cursors and signal generator off when you choose Auto Set. Once you've configured the Auto Set defaults, press Scope to remove the menu. Press AC-DC ground for Channel A to select DC coupling. Then press Auto Set. The signal you're looking at is a basic square wave describing a digital on-off signal. If your settings are correct, the voltage scale should be about 2 volts per division, and the time base about 5 milliseconds per division. Let's see how changing the frequency affects the waveform. Rotate the frequency dial on your simulator clockwise. This reduces the number of pulses per second, or pulse rate. That's what frequency is, pulse rate. Reducing the pulse rate decreases the frequency. When diagnosing a square wave signal, look at the signal's amplitude. The upper horizontal line should reach the reference voltage, the lower line should drop to within 600 millivolts of ground, and the transitions should have a clean vertical drop. Now you're ready to go to your workbook and perform the simulator exercise in Lesson 2. Make sure you're thoroughly familiar with both procedures before going on in the video. Now stop the tape and go to the simulator exercise for Lesson 2 in your workbook. In this exercise, you'll use Scopemeter's meter function to check a Ford map sensor's frequency signal. In addition, you'll see how Scopemeter's record and min-max features can capture signal glitches. Turn Scopemeter on and back probe the map sensor's signal output wire with the back probe pins included with Scopemeter. The signal wire goes to the middle terminal on the sensor. Connect the channel A probe to the back probe pin. Connect the ground lead to a good ground and turn the ignition switch on. Set channel A to DC coupling and press auto set. The signal displayed is a 50% duty cycle. That is, the positive pulse and the ground pulse are equal. So the average voltage signal should be half the 5-volt reference signal. With Scopemeter, you can actually watch the map sensor voltage rise and fall. You can measure the reference voltage, make sure the lower signal is nearly 0 volts, and tell at a glance that the duty cycle is roughly 50%. Sometimes a sensor or circuit can experience a momentary glitch or signal change. Press the min-max soft key. Scopemeter's 40 nanosecond glitch capture and min-max feature increase the sampling rate to its maximum level, making Scopemeter capable of capturing and displaying a glitch as short as 40 billionths of a second. The question is, will you be watching the display when that glitch shows up? Normally, each trace on the scope display erases the trace drawn before it. With Scopemeter's record feature, you don't have to watch the display every second. When record is on, every trace remains on display. Each subsequent trace adds to the display, so a momentary glitch would still be there when you looked again. Allow the trace to continue with record and min-max activated. Now tap gently on the map sensor. If a glitch occurs while you're tapping on the sensor, it'll remain on the display for you to see. Try this procedure under a few different conditions: heat, cold, loose wires or bad connections. All can affect the map sensor signal. Now let's use the meter function to see that changing the frequency doesn't change the voltage or duty cycle. Turn record and min-max off. Remove the vacuum hose from the map sensor and attach a hand vacuum pump to the nipple. Press meter, then press the DC volt soft key. Press the meter display mode soft key and activate duty percent negative. That sets Scopemeter to measure the percentage of time the signal is grounded. Now turn off the trace display to enlarge the frequency and duty cycle readouts. Press the meter display mode soft key again and turn off trace display. Now you can see the voltage, duty cycle, and frequency clearly at the same time. As we said earlier, the signal voltage output is roughly half of the 5-volt reference signal. The frequency should be about 159 hertz at sea level. Apply 18 inches of vacuum. Notice that the frequency changes, but the average voltage and duty cycles stay about the same. The ratio between the on time and the off time remains constant. The only thing changing is the number of pulses per second. At 18 inches, the frequency drops to about 109 hertz. Map sensors are not the only sensors that produce a frequency signal. Another common use for Scopemeter's frequency measuring capabilities is for diagnosing optical distributors. Several manufacturers, including Mitsubishi, Nissan, Chrysler, and GM, use an optical distributor to develop the ignition reference pulses necessary to run their engines. These distributors use LEDs and optical pickups with a rotor disc or interrupter between them. The disc has 2 rows of openings which produce 2 different signals. The low-resolution signal has the same number of openings as the engine cylinders. 6-cylinder engines have 6 openings, 4-cylinder engines have 4 openings. The high-resolution signal gives the computer a precise signal indicating crankshaft position. This signal is divided into 360 parts. The computer receives a signal every 2 degrees the crankshaft turns. By analyzing these 2 signals, the computer controls ignition timing and fuel delivery accurately. Scopemeter provides an easy way to examine these 2 signals. You'll start by checking the high-resolution signal. Connect the channel A probe to the high-resolution signal wire. A wiring diagram should help you find the wire. Connect the ground lead to a good vehicle ground. Turn Scopemeter on and press Scope. Make sure you're set to DC coupling. Start the engine and press Auto Set. Since the signal varies frequency based on engine RPM, the signal should open up as the engine warms and idle speed drops. If necessary, you can readjust the time base or press Auto Set again. If you're diagnosing an engine that won't start, press Auto Set while the engine's cranking. If the distributor is producing a high-resolution signal, you should see a square wave. The on-time pulses should reach within 600 millivolts of ground, and the off-time pulses at reference voltage. The transition should be clean and vertical. Now let's look at the low-resolution signal. The setup for this signal should be identical except for the time base. Set the time base to 10 milliseconds if the engine runs, 20 milliseconds for checking the system during cranking. Probe the low-resolution signal wire with the channel A probe and start the engine. Adjust the waveform to show between 2 and 4 cycles. The diagnosis for this signal is the same as for the high-resolution signal: ground, reference voltage, and good clean transitions. In this lesson, you learned how to diagnose and display a basic pulse train, and you saw how Scopemeter's meter mode can display voltage, frequency, and duty cycle. Now you're ready to perform the on-car exercises for Lesson 2 in your workbook. Once you finish the exercises, answer the review questions at the end of the lesson. If you aren't comfortable with the information covered in this lesson, go back and review those sections giving you trouble. Make sure you're thoroughly familiar with the procedures covered in Lesson 2 before going on in the program. In the next lesson, you'll look at pulse trains with a variable pulse width. Now, stop the tape and go to the on-car exercises for Lesson 2 in your workbook. In this lesson, you'll look at a pulse train with a fixed frequency, fixed amplitude, but a variable pulse width or duty cycle. The most familiar example of a variable duty cycle is a mixture control solenoid circuit. Variable pulse width solenoids cycle the same number of times per second. What changes is the ratio of on-time to off-time. As on-time increases, off-time decreases by the same amount. You'll view these signals with Scopemeter, and you'll use Scopemeter's cursors to measure the duty cycle. In this exercise, you'll learn how to freeze the display and use Scopemeter's cursors to measure and display a signal's pulse width. Set the simulator is shown in the simulator exercise for Lesson 3 in your workbook. This should give you about a 50% duty cycle. Connect Scopemeter to the simulator. Turn Scopemeter on and press Scope. Press the trigger at 50% soft key. That sets the trigger level midway between the highest and lowest voltage levels being displayed. Sort of an auto set for trigger. Adjust the voltage scale and time base until your waveform looks like this one. You may have to reset the trigger after adjusting the voltage scale. This waveform is about a 50% duty cycle. That is, the on-time and off-time are about equal. By rotating the pulse width knob clockwise, you can watch as the on-time decreases and off-time increases. Remember, since most automobile computers apply ground to energize a circuit, the on-time is the lower pulse. Rotating the dial counterclockwise reverses the on-time to off-time ratio. Now let's use Scopemeter's cursors to measure the duty cycle. Center the pulse width dial to adjust the duty cycle to about 50%. Press Hold Run to freeze the display. Press Cursor Data. Then press the function soft key to open the cursor function pop-up menu. Since you're going to measure a time difference, activate delta time. Delta means change in, so delta time is the change in time. That's what you'll measure to determine the change in pulse width, a time change. Press the function soft key again to get rid of the pop-up menu. Cursors and normal should be highlighted. Press cursor 1 to align the left cursor with the falling edge of one cycle. Then press cursor 2 to align the right cursor with the falling edge of the next cycle. The cursors are framing one complete cycle. Press the normal, delta, percent soft key to highlight percent. That assigns a value of 100% to the time between cursors. Now align cursor 2 with the rising edge of the pulse so the cursors frame the negative pulse. As you move the cursor, notice how the time percentage changes. With cursor 2 on top of the rising edge of the pulse, the percentage displayed is the duty cycle, or percentage of on time, on a ground-controlled circuit signal. Now you're ready to perform the simulator exercise for Lesson 3 in your workbook. Make sure you're thoroughly familiar with both procedures before going on in the video. Now stop the tape and go to the simulator exercise for Lesson 3 in your workbook. By this time, you should be familiar with variable duty cycle signals and measuring their on time using Scopemeter's cursors. Now you'll learn how to use Scopemeter to display and measure the pulse width of a carburetor mixture control solenoid. Connect the channel A probe to the computer side of the MC solenoid. On most vehicles, that'll be the solenoid ground. You can use Scopemeter's meter mode to find the ground circuit. Unplug the solenoid and turn the ignition key on. Set Scopemeter to the meter mode and probe the wires one at a time. One should show system voltage. The other wire is the ground circuit. On GMs, you can attach the probe to the dwell test terminal. Connect the ground lead to a good vehicle ground. Turn Scopemeter on and start the engine. First, set the ground level to the second horizontal division from the bottom of the display. Enter the scope mode and set channel A to ground by pressing AC/DC ground for channel A. Use channel A's move to lower the ground trace to the second horizontal division mark from the bottom. Then change the coupling from ground to DC. Set the trigger level to 50%. Adjust the voltage scale and time base until your waveform looks like this. Remember, you may have to readjust the trigger level after adjusting the voltage scale. Now, examine the waveform. Remember, dwell changes are nothing more than changes in pulse width. In closed loop, the computer responds to changes in the fuel mixture by varying the pulse width. The setup for this exercise will be useful in the shop for diagnostic procedures. Freeze the signal and save this setup to setup memory 2. To check the computer's ability to adjust the fuel mixture, try this again a couple of different ways. Close the choke and check the pulse width. That forces the mixture to become rich. The pulse width should increase, trying to force the mixture lean. Then try checking the pulse width again, this time with a vacuum leak, creating a lean mixture. See how the pulse width changes? If the system's working correctly, the pulse width should decrease. The pulse width change is identical to the dwell change you're already familiar with. But now you're watching the actual voltage pulses as they happen, instead of just an average change. What characteristics are you looking for in this waveform? To begin with, the signal should reach battery voltage during off time and drop to within 600 millivolts of ground during on time. Use your cursors to check this. Choose the Voltage at 1 feature from the Cursor Function menu. That lets Scopemeter display the waveform's voltage precisely beneath cursor 1. Move the cursor over the upper pulse. Scopemeter shows you the voltage in the circuit. Now move the cursor over the lower pulse. The voltage displayed should be within 600 millivolts of ground. Voltage levels aren't the only characteristics you're looking for. Check the voltage transitions. They should be clean and vertical. Voltage spikes are often normal on MC solenoid waveforms. If the circuit doesn't have a clamping diode or resistor, expect a spike when the solenoid de-energizes. Now that you know how to view and measure variable pulse width signals using Scopemeter, you're ready to perform the on-car exercises for Lesson 3 in your workbook. Once you finish the exercises, answer the review questions at the end of the lesson. If you aren't comfortable with the material covered in this lesson, go back and review those sections giving you trouble. Make sure you're thoroughly familiar with the procedures covered in Lesson 3 before going on in the program. In the next lesson, you'll look at a pulse train with a variable frequency and pulse width. Now stop the tape and go to the on-car exercises for Lesson 3 in your workbook. So far, you've used Scopemeter to display and measure two pulse train characteristics, variable frequency and variable pulse width. Now you'll look at a pulse train signal that varies in both frequency and pulse width. Ford spout signal on computer-controlled dwell ignition systems. The spout, or spark output signal, is a computer-generated dwell and timing advance signal. The computer uses the pip signal from the pip sensor or crank sensor and adds the necessary dwell and timing advance to create the spout signal. The additional dwell and timing advance change the pulse width. Frequency changes are a direct result of engine speed changes. The higher the engine RPM, the higher the frequency. In this lesson, you'll view two pip and spout waveforms, one at idle, the other at 2,000 RPM, using Scopemeter's dual trace feature. Then you'll compare their frequencies and pulse widths using Scopemeter's cursors. To examine the relationship between the pip and spout signals, we'll be using a Ford with computer-controlled dwell and distributorless ignition. A schematic will show which module wires are the pip and spout signal wires. Connect the channel A probe to the spout signal wire and the channel B probe to the pip signal wire. You can back probe the connector at the ignition module with your back probe pins. Or use a breakout box to attach Scopemeter's probes to these circuits. Connect the ground lead to a good vehicle ground and turn Scopemeter on. Press Chan AB, then press soft key number 2 to highlight B. That turns the channel B trace on. Start the engine. Once the engine reaches normal operating temperature, set Scopemeter to the scope mode with both channels set for DC, trigger at 50%. Since you're going to view two waveforms on the display at once, press channel A's move to raise the channel A trace to the top half of the display. Then press channel B's move to lower the channel B trace to the bottom. Adjust the voltage scale for each channel and set the time base to display between 2 and 4 pulses. Remember, you may have to readjust the trigger level after setting the voltage scale. Press Hold Run to freeze the display. Press channel B's move to overlay the pip signal onto the spout signal. Now the similarity between the signals becomes obvious. The ECA uses the pip signal as a base timing signal and uses it to create the spout signal. The lower horizontal lines on the spout signal indicate ignition dwell. The ECA adjusts ignition dwell by adjusting the falling edge of the dwell pulse, changing when dwell begins. The wide space between the pip's falling edge and the spout's falling edge indicates a short dwell at idle. The rising edge of the spout pulse is the timing signal, the signal that tells the module to fire the coil. The ECA adjusts this signal from the base timing signal to create timing advance. As you might expect, the signal at idle shows very little advance. Now let's use Scopemeter's cursors to measure the signal frequency. Separate the waveforms. Press Cursor Data. Then press the Function soft key to bring up the Cursor Function pop-up menu. Activate Delta Time and Frequency and close the menu. Source A, cursor, and normal should be highlighted. Source A means the signal you're measuring is on channel A. To measure channel A's frequency, move cursor 1 all the way to the left side of the display. Cursor 2 to the right side. The right menu displays channel A's frequency. Record your results for comparison later. Let's compare that frequency to channel B. Press the source soft key to highlight B. Now the frequency shown is channel B's. Both channels should have almost the identical frequency, proving there's a one-to-one relationship between the pip and spout signals. Now you can use cursors to measure the pulse width percentage of these signals. Start with the pip signal. Align cursor 1 with the falling edge of one of the pulses. Cursor 2 with the falling edge of the next pulse. You may have to use move to move the waveform over a bit to align the cursors. Highlight percent. This assigns a 100% value to the time between the cursors. Now align cursor 2 with the rising edge of the pulse. Record the percentage of pulse width displayed on the right menu. As you probably guessed by now, the pulse width for the pip signal is roughly 50%. Only the frequency changes with engine speed. The percentage of coil on time is normally presented in degrees of dwell. Your workbook has a chart and a formula for converting percentage of pulse width to degrees of dwell. Now measure the pulse width for the spout signal on channel A. Set the cursors to display one full pulse. And press the normal, delta, percent soft key 3 times to highlight percent again. That resets the value between the cursors to 100%. Align cursor 1 with the falling edge of the pulse and record the percentage of pulse width. The setup for this exercise will be useful in the shop for diagnostic procedures. Save it to setup memory 3. Now measure the pip and spout signals again, this time at 2,000 RPM, and compare them to the signals at idle. Press Hold Run to start the display again. Raise the engine speed to 2,000 RPM. Adjust the time base to display 1 to 2 pulses and freeze the display. Now let's compare the pip and spout signals. Raise the pip signal until it almost overlays the spout signal. You can see the increase in the timing advance, much greater than at idle speed. The falling edge of the spout pulse is much closer to the pip's falling edge, indicating a longer dwell and increasing coil saturation. Both of these conditions are just what you'd expect when comparing the timing advance and dwell at idle to 2,000 RPM. You can follow the same procedures as before for measuring frequency and the percentage of pulse width. As you might expect, frequency should be almost identical for both pip and spout, but considerably higher than at idle. The pip signal is a variable frequency, fixed pulse width signal, since the pip signal is from a fixed mechanical sensor. Its pulse width percentage at 2,000 RPM should be about the same as its pulse width at idle. The spout signal is a variable frequency, variable pulse width signal. Both pulse width, percentage, and frequency should be different at idle than at 2,000 RPM. You may run into a situation where the pip and spout signals are identical. This indicates the module isn't receiving a spout signal, so the ignition module substitutes the pip signal to allow the car to run. This could indicate an ECA, computer system, or wiring problem, or an open spout connector. Regardless of the reason, the vehicle will be running at base timing. Complaints will range from no power to poor gas mileage. When examining these waveforms, make sure that both the reference voltage and ground reach the proper voltage levels, and see that the voltage transitions are straight and clean. A signature on the reference portion of the signal is normal in the pip and spout waveforms. It doesn't interfere with the system's operation. The pip and spout signals from a distributorless system look a little different than those from a vehicle with a distributor. Your workbook shows examples of each of these waveforms for diagnosis. In this lesson, you learned how to use Scopemeter's cursors to measure frequency and pulse width. Now you're ready to perform the on-car exercises for Lesson 4 in your workbook. Once you finish the exercises, answer the review questions at the end of the lesson. If you aren't comfortable with the information covered in this lesson, go back and review those sections giving you trouble. Make sure you're thoroughly familiar with the procedures covered in Lesson 4 before going on in the program. In the next lesson, you'll use the cursors to measure injector on time and use Scopemeter to examine and diagnose fuel injector circuits. Now, stop the tape and go to the on-car exercises for Lesson 4 in your workbook. Most cars built today use some form of electronic fuel injection to deliver fuel to the engine. For diagnostic purposes, there are two main methods of controlling electronic fuel injection: group injection and independent driver fuel injection, which includes sequential and throttle body injection. All of these injection types have one thing in common. They all vary fuel delivery by increasing or decreasing injector on time. Increasing injector on time increases fuel delivery. Your Scopemeter allows you to measure the precise injector on time and check the injector's electrical condition and operation by examining the waveform produced when the injector fires. So far, you've used Scopemeter's cursors to measure frequency and percentage of pulse width. In this lesson, you're going to use them to measure the actual on time for electronic fuel injectors in milliseconds. You'll see how changing injector on time adjusts fuel flow. And you'll use Scopemeter's dual trace feature to compare the injector pulses with the signal that triggers them. You'll learn about trigger delay, a feature that allows you to tell Scopemeter to begin drawing the trace before or after the voltage crosses the trigger level. For example, setting the trigger delay to -1 tells Scopemeter to begin drawing the trace one time division before voltage crosses the trigger. That moves the waveform one division to the right, which makes viewing some signals easier. This is a unique feature of a digital oscilloscope. Scopemeter allows you to set the trigger delay from -20 divisions to +640 divisions. In the next exercise, you'll examine a simulated injector waveform, learn to use Scopemeter's cursors to measure and display injector on time, and you'll compare waveforms by storing and retrieving them from one of Scopemeter's 8 waveform memory locations. Adjust the simulator to the settings shown in the simulator exercise for Lesson 5 in your workbook. Set Scopemeter to display DC coupling with the ground trace aligned with the bottom voltage division. Adjust the trigger level to about 500 millivolts negative slope. That sets the trace to begin with the injector on time. Now move the waveform to the right 2 time divisions by setting the trigger delay to -2. Press the delay soft key, use the up-down arrow keys to highlight time delay, then press enter to activate. The delay value will be displayed in the right menu area. Use the up-down arrow keys to set the delay to -2. Adjust the voltage scale and time base to display 1 or 2 waveform pulses. You may have to reset the trigger level after adjusting the voltage scale. Now you're ready to measure the waveform's on time. The falling edge of the pulse is the beginning of the on time, energizing the injector. The rising edge ends the on time, de-energizing the injector. The voltage spike is created when the injector's magnetic field collapses after the current shuts off. Freeze the display. Turn the cursors on and choose the function soft key. Deactivate everything except the delta time function. Use the right side soft key to highlight normal and use the cursors to measure the on-time pulse. Align cursor 1 with the falling edge of the pulse, cursor 2 with the rising edge. The on-time will be displayed on the right menu. Press hold run to display a live waveform. Adjust the pulse width dial, and practice measuring the pulse width using the cursors. Now you're ready to perform the simulator exercise for Lesson 5 in your workbook. Try this procedure a few times until you feel comfortable with using the cursors to measure time differences. Make sure you're thoroughly familiar with these procedures before going on in the video. Now stop the tape and go to the simulator exercise for Lesson 5 in your workbook. By now you should be familiar with trigger delay and with using the cursors to measure time. Now you're ready to look at some real fuel injector waveforms. Connect the channel A probe to the negative side of a fuel injector and the ground lead to a good ground. Adjust the ground level to the lowest voltage division and set Scopemeter to read DC coupling. Set trigger to about 6 volts negative slope and the trigger delay to -2. Start the engine and allow it to reach normal operating temperature. Adjust the voltage scale and time base to display one on-time pulse. You may have to reset the trigger level after adjusting the voltage scale. There are 3 different types of electrical circuits used to operate fuel injectors: saturated driver, peak and hold, and pulse modulated. And each injector circuit requires measuring on time differently. If the vehicle you're working on has a conventional or saturated driver injection system, the waveform should look something like this. The falling edge is the beginning of the injector's on time. The voltage spike results from the injector's magnetic field collapsing after the current shuts off, ending the injector on time. On a peak and hold injector circuit, the voltage doesn't release all the way. Instead, injector voltage returns to slightly less than system voltage. That keeps the injector energized throughout the injector on time at reduced current flow. When the current releases, the signal returns to system voltage. When measuring the on time, measure from the falling edge to the second rising edge of the waveform. This is where the injector shuts off completely. On a pulse-modulated injector, an initial high current pulse opens the injector. Then the ground circuit begins to pulse rapidly, extending injector on time. When the pulses stop, the signal returns to battery voltage. Measure the injector on time from the falling vertical edge to the end of the pulsed section of the waveform. Diagnosing injector waveforms is mostly a matter of experience and comparison. By viewing as many good injector waveforms as possible, bad ones become obvious immediately. One of the difficulties with diagnosing an injector based on its waveform is determining whether the problem's in the injector or the ECM driver transistor. Both can make the injector waveform look abnormal. How can you tell which is causing the problem? To isolate the problem, you must know which injection system you're working on. With group injection, each driver in the computer fires more than one injector. Either a faulty injector or bad driver can disrupt the waveform for all of the injectors in that group. On sequential or throttle body injection, each injector has its own driver in the computer. You must check each injector's waveform individually. Measuring injector on time allows you to check the computer's responses to input changes, such as oxygen sensor voltage or changes in sensor output from the throttle position sensor or map sensor. The setup for this exercise will be useful in the shop for diagnostic procedures. Save it to setup memory 4. Another feature that makes comparing waveforms easy is Scopemeter's waveform memory. You can store up to 8 waveforms and display up to 4 at once. Or you can compare a live waveform to one stored in memory. To store a waveform being displayed, freeze it and press Waveform. Press the Copy soft key and choose which channel's waveform you want to save in memory. Press Enter, and another pop-up menu lets you choose where to store the waveform. Every time you store a waveform in a memory location, anything that was there before is erased. A small dot next to the memory listing tells you there's a waveform stored in that memory location. Once you've stored waveforms, you can recall and display up to 4 stored waveforms or a combination of stored and live waveforms. Press Waveform, then press the waveform on-off soft key to display a pop-up menu of waveform memories. Choose the memory you want to display and press Enter. A large black dot shows you if a memory is being displayed. Repeat the procedure to display up to 4 memories at once. To turn a waveform off, choose it the same way you did to turn it on. To eliminate the pop-up menu, press the waveform on-off soft key. In the next exercise, you'll use Scopemeter's dual trace feature to view an injector signal and the ignition reference signal to examine the relationship between those signals. Vehicles with electronic fuel injection use an ignition reference signal to time the injector pulses. So if the engine shuts off because the injectors lost their signal, it could have an ECM problem, or the ECM could have lost its ignition reference signal. You can use Scopemeter's dual trace feature to track the relationship between these signals. For this test, we'll be using a 1992 Olds with a 3800 engine. Connect the channel A probe to the negative side of a fuel injector and the channel B probe to the ignition reference input to the computer. Connect the ground lead to a good ground. Start the engine and set both channels to display DC coupling. And adjust the waveforms to look like these. Look for a relationship between the ignition reference signal and the injector signal. There may be a 1-to-1 relationship, a 2-to-1, even an 8-to-1. It doesn't matter, just so you see a relationship. On this vehicle, the relationship is 6-to-1. That's because the ECM uses the reference pulse to time the injectors. If it doesn't see a reference pulse, it doesn't know when to fire the injectors. Suppose you had a car that's cutting out on the road. How can you tell if the problem's ECM related or if the ECM's losing its ignition reference pulse? Turn off free run and make sure Capture 20 divisions is highlighted. 20 divisions effectively doubles the width of the display. Use Move to view the second half of the display. Increase the time base to display 3 to 4 injector pulses. Trigger on A with a delay of -1. When the injector signal drops out, the trace will continue to the end of the display and stop. Since free run is off, losing the trigger forces the display to show the last waveform traced. If the reference pulse and injector pulse disappear together, the computer stopped receiving a reference pulse. Look for an ignition problem, possibly a crank sensor, distributor pickup, module, or wiring problem. At this point, you'll need to do further testing to see why the computer lost its ignition reference pulse. But if only the injector pulse shuts off, there will still be a few ignition reference pulses before the engine quits. You know the problem's in the computer, its related circuits, or the injector's lost its power feed. The setup for this exercise will be useful in the shop for diagnostic procedures. Save it to set up memory 5. Scopemeter's zoom feature allows you to take a closer look at a waveform. Use Move to center the waveform you wish to view in the display, and press the up arrow key to zoom in on that area. Zoom keeps the waveform centered. Each time you use zoom, the time base and trigger delay reflect the change. Press the down arrow to move back to your starting point, or zoom out to look at a larger part of the waveform. Now you're ready to perform the on-car exercises for Lesson 5 in your workbook. Once you finish the exercises, answer the review questions at the end of the lesson. If you're not comfortable with the information covered in this lesson, go back and review those sections giving you trouble. Make sure you're thoroughly familiar with the procedures covered in Lesson 5 before going on in the program. Now stop the tape and go to the on-car exercises for Lesson 5 in your workbook. In this lesson, you're going to look at pulse amplitude modulated solenoids, which include Ford idle air bypass valves and other Ford pulsed solenoids. These signals not only vary in frequency and pulse width, but also amplitude. That is, the voltage of the signal changes, which changes how far the valve opens. If the voltage pulses between 9 and 12 volts, the valve is nearly closed. If the voltage pulses between 1 and 4 volts, the valve is open nearly all the way. In addition, the closer the voltage level is to 0 or 12 volts, the slower the frequency. At higher voltage levels, pulse width will be shorter. At lower voltage levels, pulse width will be longer. In this exercise, you'll see how to use Scopemeter to view a Ford idle air bypass signal and see what that signal tells us about the engine's adjustments and condition. Start with a cold engine so you can see how the idle air bypass signal changes as the engine warms up. Connect the channel A probe to the negative side of the idle air valve and the ground lead to a good ground. Turn Scopemeter on. Set the ground level to the division nearest the bottom of the display. Then choose DC. Since you'll be looking at a signal ranging from 0 to about 14 volts, set the voltage scale to 2 volts per division. That'll keep the waveform on the display at all times. Set the time base to about 5 milliseconds per division. Start the engine, set the trigger to 50%, and watch the waveform as the engine warms up. When the engine's cold, the voltage signal should remain low, keeping cold idle speeds high. As the engine warms, voltage should slowly increase and idle speeds decrease. You'll have to reset the trigger level as voltages increase or you'll lose trigger and the signal will begin to wander. Your Scopemeter makes diagnosing this signal easier. Switch to the meter mode and select DC volts and record. Use the voltage signal to view the minimum, maximum, and average voltage levels. Normal voltage levels should range between 7 to 11 volts at idle on a warmed-up engine. If the voltage stays below 7 volts, the ECA is working too hard to maintain the idle speed. You may have a sticking or damaged idle air bypass valve, a misadjusted or dirty throttle plate, clogged valve passage, or there's an engine performance problem. If the voltage levels stay above 11 volts, but the idle speed won't remain low enough, look for a vacuum leak or a misadjusted throttle plate. With this type of waveform, the signal doesn't always go to ground, and the amplitude varies. The transitions aren't necessarily vertical and may be sawtoothed or curved by solenoid inductance. The setup for this exercise will be useful in the shop for diagnostic procedures. Save it to Setup Memory 6. So far, you've learned how to use Scopemeter's cursors to measure frequency, pulse width, and time change. Now you're ready to perform the on-car exercises for Lesson 6 in your workbook. Once you finish the exercises, answer the review questions at the end of the lesson. If you're not comfortable with the information covered in this lesson, go back and review those sections giving you trouble. Make sure you're thoroughly familiar with the procedures covered in Lesson 6 before going on in the program. In Lesson 7, you'll learn about 3 more cursor functions: peak to peak, minimum peak, and maximum peak. Now stop the tape and go to the on-car exercises for Lesson 6 in your workbook. In this lesson, you'll see how to use Scopemeter to map a variable voltage. At the same time, you'll learn about 3 new cursor functions: maximum peak, minimum peak, and peak to peak. These functions enable Scopemeter to measure the highest and lowest voltages displayed and the differences between the voltages. For this lesson, you'll map the voltage changes of a zirconium-type oxygen sensor. This sensor is a type of battery that produces between 0 and 1 volt based on the amount of oxygen in the exhaust system. You'll use Scopemeter to map the voltage changes, to measure the voltage peaks, and the difference between the high and low voltage levels. Since the oxygen sensor produces between 0 and 1 volt, set Scopemeter's voltage scale to 200 millivolts per division with about a 450 millivolt trigger level. A time base of about 200 milliseconds is a good starting point, though you may have to readjust that later. Lower the ground level to midway between the first and second divisions at the bottom of the display. That makes the center grid line equal to 500 millivolts, roughly the division between lean and rich. Then switch to DC coupling. Start the engine and run it at 2,000 RPM until the oxygen sensor voltage starts to fluctuate above and below the center line. That tells you the system's in closed loop. The signal you're watching is oxygen sensor voltage as it rises and falls, tracing the mixture changes from rich to lean. Goose the throttle and watch the voltage follow the mixture. Rich during acceleration, lean while decelerating. Remember, the voltage should waver above half a volt as often as it does below half a volt at a constant throttle opening. If the signal remains high more often, the engine's running rich. If the signal remains low more often, the engine's running lean. Now let's use Scopemeter's cursors to measure voltage levels. Hold the throttle at 2,000 RPM, freeze the waveform, and press Cursor Data. Press the Function Soft key to display the function pop-up menu. Deactivate anything else that may be on. Then activate Peak to Peak, Max Peak, and Min Peak. Adjust the cursors to frame the waveform and read the voltage levels. Min peak gives you the lowest voltage reading displayed. Max peak gives you the highest voltage. Peak to peak shows you the difference between the highest and lowest voltage. That is, the range between the voltage peaks. A good oxygen sensor on a system that's working properly should range from less than 200 millivolts to at least 700 millivolts. So the peak-to-peak voltage should be at least 500 millivolts. If the oxygen sensor voltage doesn't range between these levels, the sensor could be bad or the system may not be working properly. The setup for this exercise will be useful in the shop for diagnostic procedures. Save it to setup memory 7. So far, you've learned how to use Scopemeter to view and diagnose expected voltage signals. Now you're ready to perform the on-car exercises for Lesson 7 in your workbook. Once you finish the exercises, answer the review questions at the end of the lesson. If you aren't comfortable with the information covered in this lesson, go back and review those sections giving you trouble. Make sure you're thoroughly familiar with the procedures covered in Lesson 7 before going on in the program. In Lesson 8, you'll look at signals that shouldn't be there, electrical noise. Now, stop the tape and go to the on-car exercises for Lesson 7 in your workbook. What do these three conditions have in common? A popping noise in the radio, an engine stumble, and a flickering check engine light. Give up? They're all symptoms of electrical noise. Electrical noise is any kind of stray electrical signal that may interfere with the performance of an electrical device. Automobile manufacturers go to great lengths to reduce or eliminate electrical noise. Resistor plugs and resistance ignition wires are two common methods for reducing electrical noise from the ignition system. Diodes, resistors, capacitors, and shielded cables are all devices used for controlling electrical noise. In this lesson, you'll use Scopemeter to identify a couple of common sources of electrical noise: air conditioning compressor clutches and blower motors, and compare noisy signals with properly damped waveforms. One of the most common and most often overlooked electrical noise suppression devices is the clamping diode in the AC compressor electrical connector. In this exercise, you'll learn how to use Scopemeter to capture the voltage spike developed when a compressor clutch with a bad or missing diode de-energizes. Connect the channel A probe to the positive side of the connector. Connect the ground lead to a good vehicle ground. Raise the ground level to the second division from the top. Choose DC coupling, 20 volts per division. Set the time base to 5 milliseconds to start. You may want to adjust that later. Since the voltage spike we'll be viewing is negative, choose a negative slope and negative 20 volts trigger level. Delay the trigger by 2 divisions and press Scope to get back to the Scope menu. Use the soft keys to choose single and turn free run off. These settings allow Scopemeter to capture one event, but only after the voltage crosses the trigger level. Make sure no trig is flashing. If it says hold, press hold run. Start the engine and turn the air conditioning on. The compressor clutch must be engaged to run this test. Since the voltage hasn't dropped below negative 20 volts, Scopemeter shouldn't display a waveform yet. Now turn the air conditioner off. If the clamping diode is bad or isn't there, a voltage spike occurs. If the diode's okay, you won't see a waveform displayed. There's another feature of Scopemeter you could use to look for these spikes: A-invert. A-invert effectively flips the display. The voltage level and slope are still negative, but now negative is up. The setup for this exercise will be useful in the shop for diagnostic procedures. Save it to setup memory 8. Now let's look at a more consistent electrical noise developed by electric motors. In this exercise, you'll use Scopemeter to look at electrical noise riding on a standard DC signal. The common cause for this kind of electrical noise is an electric blower motor. As the blower runs, it develops an AC voltage that rides along the DC voltage line. By setting Scopemeter to AC coupling, you're telling it to ignore the DC voltage applied to the blower motor and just display the alternating current the blower motor produces. In this exercise, you will use Scopemeter to display and measure the AC voltage a blower motor develops, and you'll learn how a capacitor reduces that electrical noise. Connect the channel A probe to the blower motor power lead, and connect the ground lead to a good vehicle ground. Adjust the ground level to the middle of the display and set Scopemeter to AC coupling. Set the scales to display 200 millivolts and about 2 milliseconds per division. Adjust trigger to positive slope, 0 volts. Turn the ignition on and set the blower motor to high. The waveform you're looking at is the AC voltage the blower motor develops as it runs. Setting Scopemeter to AC coupling filters out the DC voltage and shows only the electrical noise the blower motor produces. Try different speeds and see what happens to the waveform. See how the noise relates to the blower speed? Slower speeds may even develop more electrical noise than higher speeds. But all electric motors develop electrical noise. Capacitors and diodes keep that noise down to a minimum. The question is, how can you tell whether the waveform you're looking at indicates too much noise? You can use Scopemeter's cursors to measure the voltage output to determine whether the noise output is excessive. Freeze the display, turn the cursors on, and choose RMS from the function menu. RMS stands for root mean square, a formula that converts a varying voltage to a value comparable to DC volts. Make sure cursor and normal are highlighted. Frame the waveform in the cursors. Scopemeter should display the RMS voltage between the cursors. If the RMS voltage exceeds 300 to 500 millivolts, it could be a source of electrical noise interference. Some manufacturers offer capacitors, electrical chokes, or filters designed to reduce this electrical noise. Try checking the electrical noise with and without the capacitor and see how it affects the signal. The setup for this exercise will be useful in the shop for diagnostic procedures. Save it to Setup Memory 9. In this lesson, you learned how to check a circuit for electrical noise and what can cause it. Now you're ready to perform the on-car exercises for Lesson 8 in your workbook. Once you finish the exercises, answer the review questions at the end of the lesson. In the next lesson, you'll take a look at non-repetitive pulses using Scopemeter to perform a sensor sweep test. Now stop the tape and go to the on-car exercises for Lesson 8 in your workbook. In this lesson, you're going to use Scopemeter to measure, examine, and diagnose the output from a potentiometer. There are a number of potentiometers used in automobiles today. The most familiar is a throttle position sensor, but there are others. A vane-type airflow meter, variable height sensor, and a climate control air door position sensor, to name a few. One way to test a potentiometer is with an analog voltmeter, but the needle response is often too slow to show a glitch in the voltage. Scopemeter's 50 megahertz bandwidth and 40 nanosecond glitch capture make it the perfect tool for viewing and diagnosing potentiometers. Here's how. Set your simulator as shown in the simulator exercise for Lesson 9 in your workbook. Connect Scopemeter to the simulator and turn Scopemeter on. The pulse width knob on your simulator must be counterclockwise all the way. Set Scopemeter to the meter mode and press DC volts. Use the up-down arrow keys to choose the 30-volt scale and press record. This allows Scopemeter to display the lowest and highest voltage it sees. Rotate the pulse width dial on your simulator clockwise all the way. Scopemeter should display the minimum and maximum voltages you'll be working with for this test. Write these voltages down for use later. Rotate the simulator knob back to the full counterclockwise position and change Scopemeter to the scope mode. Set Scopemeter to single, turn free run off, and highlight Capture 10 divisions. Choose Min-Max on A. This increases the sampling rate to Scopemeter's highest level. Set the ground level to the lowest voltage division and use the higher voltage you recorded earlier to set the voltage scale. Since the simulator puts out close to 5 volts for this test and you have 6 divisions above the ground level, 1 volt per division will spread the sensor sweep over the largest area of the display. Then set channel A to DC coupling. Set the trigger level to about 100 millivolts above the minimum voltage level you recorded earlier, with a positive slope. That keeps the trace from starting until you begin the voltage sweep. Adjust the time base to about 500 milliseconds per division and set the trigger delay to begin its trace at -1 division. Make sure no trig is flashing. Now you're ready to begin your sweep test. Slowly rotate the potentiometer knob all the way clockwise and then back again. As soon as the voltage increases by 100 millivolts, Scopemeter begins its trace until it reaches the end of the display. The waveform you're looking at represents the voltage as it rises and falls when you turn the simulator knob. A good waveform should be smooth and even with no glitches. Now you're ready to perform the simulator exercise for Lesson 9 in your workbook. Make sure you're thoroughly familiar with the procedures before going on in the video. Now stop the tape and go to the simulator exercise for Lesson 9 in your workbook. In this exercise, you're going to use Scopemeter to view and diagnose a throttle position sensor. Connect the channel A probe to the signal wire from the TPS and connect the ground lead to a good ground. Turn Scopemeter on. Set it to the meter mode and use the up-down arrow keys to choose the 30-volt scale. Turn the ignition key on. press the record hard key. Press the pedal all the way to the floor and release it. Scopemeter should display the minimum and maximum voltage levels it recorded. On this car, the minimum voltage was 0.61 volts, and the maximum was 4.46 volts. You'll use these readings to set the voltage scale and trigger levels. Switch over to the scope mode and set Scopemeter to single. Turn free run off and highlight Capture 10 divisions. Activate Min-Max to raise the sampling rate to Scopemeter's maximum level. Adjust the ground level to the bottom voltage division and use the voltage readings you took to choose a value for the voltage scale. Since the maximum voltage was 4.46 volts, 1 volt per division is a good choice for the voltage scale. Choose DC coupling and set the time base to about 500 milliseconds per division. Set the trigger to about 100 millivolts above the minimum voltage. Since the minimum voltage was 0.61 volts, or 610 millivolts, you should set the trigger level to about 710 millivolts. Select positive slope and adjust trigger delay to -1. Make sure no trig is flashing. Now you're ready to start your test. With the ignition key on, slowly press the gas pedal to the floor, then slowly release it. Scopemeter should display a waveform indicating the voltage change as the throttle opening changed. The waveform should show a smooth increase to full voltage and a smooth return to base voltage. A glitch or erratic signal indicates a bad sensor. Press Hold Run to erase the display and highlight No Trig again. Set the time base to 200 milliseconds per division and press and release the pedal faster than you did in the earlier test. The signal should still be smooth and glitch-free. The setup for this exercise will be useful in the shop for diagnostic procedures. Save it to Setup Memory 10. You're only saving the fast sweep setup. You may have to adjust the time base later to perform a slow sweep test. You can use this same trigger method to monitor one signal on channel B and trigger from another signal on channel A. For example, try viewing the waveform created by the mass airflow sensor on channel B, but triggered from the TPS voltage on channel A. Neither trace begins until channel A voltage reaches its trigger level. This setup allows you to view the mass airflow sensor's response to throttle movement. In this program, we've given you a glimpse of just a few of the automotive diagnostic uses for the Fluke Scopemeter. In reality, its uses are almost limitless. In addition to the probes and test leads shown in this program, you can purchase the optional accessory kit for your Scopemeter. This kit comes with an optical computer interface that allows you to couple your Scopemeter with an IBM-compatible computer or printer. Start a library of common and not-so-common waveforms for comparing to questionable waveforms. A temperature transducer lets you use Scopemeter as a digital pyrometer, providing instant temperature readouts of cooling systems, exhaust systems, even air conditioning system temperatures. A pressure transducer allows Scopemeter to double as a vacuum pressure gauge. Read precise vacuum or pressure levels for testing engine vacuum, fuel pressures, oil pressures, even tire pressures with electronic accuracy. An AC/DC current clamp lets you use Scopemeter to measure precise current draw from solenoids, relay starters. Even check charging system output with your Scopemeter. It's easy to see how the Fluke 97 Auto Scopemeter could become the most valuable tool in your center. Scopemeter is your competitive edge, reducing your diagnostic time and improving your profitability today and in the years ahead.